Okay, and we're ready to go. We are going to talk about equations. Yes. Awesome. People love equations so much that they do things that you can only do with equations when they don't have equations. That's how much people like equations. Now I'm going to talk about it. Right? Can you just square it? No, you can't. Just square it. There's no equation. Like people just do that. I multiply by 2. You can't do that. There's no equation. If you multiply by 2, you're changing something. With equations, you get to do all the stuff you want to do as long as you're balanced with doing it. Just make sure you're kind of doing the same thing on both sides, and you're pretty much going to be okay as long as you don't do anything too crazy. So, let A be algebraic expressions. Expression A equals B is called an equation. It's called an equation because of the equal symbol. Okay? So if it doesn't have that symbol, it's not an equation. If it doesn't have that symbol, it automatically means there are some things you're not allowed to do, there are some things you are allowed to do. A equals B is a statement saying that A and B are precisely the same expressions. Or can be made to be the same. By plugging in specific values of any variables present. So we spoke about what variables were already. These are guys that their values can change based on the context, based on domains and all that stuff. And A equals B is just an expression that says these two expressions are the same thing, or we can make them the same by plugging in certain statements, certain values for the variables. For example, I can say that x squared plus 4x is equal to x times x plus 4. This is an equation. In fact, this equation is always true for every value of x. In fact, this one is always true for any value of x. Such an equation is called an identity. An equation where it's always true no matter what you do, there's no escaping it. It has to be the case that x plus 4x is going to be, x squared plus 4x is going to be x times x plus 4. An identity. Now most people see the word identity in the context of trig identities, equations that are always true no matter what angle you plug in, but identity is a larger concept. You have an equation where no matter what you do, it's always going to be true. It's called an identity. By the way, there are equations where they're never true. So if you try to set up an equation, but no matter what you do, that you can never get it to be true, that's called a contradiction, and you shouldn't do it. But in this class, we're not going to worry about that too much. So that's called an identity. Another example is I can say x plus 1 equals 3, and this is an equation, again, because of the equal sign. The value x equals 2 makes the above true. Meaning when I plug in x equals 2, both sides give me the same thing. And so if I plug in 2 plus 1, I do get something that's equal to 3. That's a true statement. There are values that will not make it true. Isn't true. So, for example, I can plug in 3 for x, and I would get 4. And this is not equal to 3. So it means that this will not be true. This is the not equal sign. Just put a slash through it. That's the not equal sign. If you want to say something isn't equal, you put the slash through it. Okay. What else do I want to tell you? Now, the values that will make an equation true, we say they belong to a certain set called the solution set of the equation. And any values, of course, that are not, make the equation not true, these do not belong to the solution set. To solve an equation, actually to solve an equation, means to find the solution set. Find me the set of all possible values that if I plug it into that equation, it makes it a true statement. This is what it means to solve an equation. So I can give you an equation and I can say, solve this equation. What do I want you to do? Find all x's that when you plug it into this statement, it makes it a true statement. And most times, this is going to be true like right up to calculus 3. So you can go with this for the next 2 years or so. After that, it's not always going to be possible to do what I'm about to say. Most times, this is done by isolating the variable. So you want to end up with something that says, so given an equation, given an equation with x's in it, you want to perform legal mathematical processes to the goal of ending up with x equals something over here, expression without x's. So once you get to this situation, you say you've solved the equation. It is solved by the x's that are over here, and that is just me telling you what the solution set is. It can be a list of things, could be one thing, could be nothing. You could have an equation that has no solution for all intents and purposes. So that's what an equation is, just saying that it's the same, that two sides, two expressions are the same thing. Potentially we need to plug in a value of a variable to make them the same. These values are called, are said to belong to the solution set, and essentially we want to be able to, given an equation, get to a situation where I can tell you what the variables need to be, what are the values that are in the solution set. And that's it in terms of the overarching ideas here, but we are going to get specific. I'm going to talk about various kinds of equations. But probably before that, maybe I should tell you about what are the legal math processes. So maybe I should talk about the properties of variables. So we're going to use 4 things in general for us. 4 properties. Will be useful in solving equations. One. So here's the thing. So you can add something to both sides. That's the first thing I want to mention. So if A equals B, then A plus C equals B plus C will be true. And i.e., you can add or subtract. The C could be a negative thing. From both sides. And maintain the solution set. So these two things will not change the solution set. The variables that work over here, the exact same ones will actually work over there. But you might want to add or subtract something to get into a more convenient form, i.e. this form. This is a convenient form right here. And so to get there, one thing you could potentially do is add something to both sides. 2. If A equals B, then AC equals BC. You can multiply both sides by the same thing. I'm not going to write that out, sort of get the idea. And if AC equals BC, and your C is not equal to 0, then your A must be equal to B. Now that's something very specific to us. That actually is not true once you get to some higher mathematics. But this one is often referred to as the cancellation law. You can kind of cancel the C's on both sides, or divide both sides by C and cancel them. You can only do it if your C is not 0. And the last one, this is the one we're going to use a lot. It's going to be very, very useful, especially in the nonlinear case. And 4, it's called the 0 factor property. Emphasis on the word 0. It works specifically with the number 0. It does not work in any other context, at least not in the real numbers. Again, this is something that's only true at like the elementary level. You start getting too complicated, that this also doesn't work. But for us, it's going to work all the time. It's going to be awesome. So basically what this says is if your A times B equal to 0, then either A equals 0 or B equals 0. Or potentially both, but one or the other must be 0. The only way to multiply two things and get 0 is if one of the things is 0. That's called the 0 factor property, right? So the A and the B here are called the factors. This is a multiplication here. If you have a factor of things multiplying, giving you 0, one of the factors must be 0. This is called the 0 factor property. It does not work with any other number on this side other than 0. Okay? If there's any other number other than 0, there's an infinite number of possibilities, right? So which I see students do things like this all the time. Ignoring the 0 factor property, emphasis on 0. if A times B equals, say, 1, no similar property is true. Or anything else. Other than 0. So if you have two things equal 1, then yeah, both could be 1, but it also could be this is 2 and that's a half. It could also be this is pi, that's 1 over pi, right? There are tons of ways to get 1. If there's a 0, there's not tons of ways. There are 2 ways, right? Either this guy's going to be 0 or that guy's going to be 0. It's not true in general. The above has infinite possibilities. So that let's just make that clear, because I see that from time to time. So those are the legal moves. At any given time, if I give you an equation, you can take advantage of one of or several of these properties to actually bring the equation to a point where you can tell what the solution set is. This usually means bringing it to a point where you have the variable equals something that doesn't have the variable in it. Let's talk about important types of equations for us. We're going to talk about linear equations. We are going to talk about nonlinear equations. Under nonlinear equations, we'll treat this as a separate topic, but it actually falls under this category. We're going to specifically talk about quadratic equations. Those are very useful. We're going to talk about radical equations. And I think that's all the kinds of equations I want. I mean, equations with rational expressions also, but they can also fall under nonlinear. Maybe I'll just put them here. Equations with rational expressions. Which is what we were talking about the last time. Yesterday in the class before. Monday in the class before. So, let's begin. Linear equations, let's start there. It's the easiest kind of equation. The linear equation in the variable x is an equation that can be written in the form. So it's either given like this, or you can write it like this: ax plus b equals c. This is called a linear equation, where a, b, c are constants, a not equal to 0. It's called a linear equation. To solve, isolate x by using PEMDAS and performing opposite operations. Opposite operations in the sense that we think of subtraction as the opposite of addition, multiplication is the opposite of division, that kind of thing. So if you have something being added together and you don't want it being added anymore, subtract it from both sides. You have to obey the 4 previous properties. It's supposed to be cold today. It's just so warm and now I'm burning up. Maybe they turned up the heat or something. Okay. One thing I want you to note, I've said this before, but I should write it down again. When isolating. Separate the terms with the variable from the terms without the variable. First. And remember, let's say I have something like 2x plus 1 equals, I don't know, 5. What you would do here is, remember that multiplication and division, these are kind of a joining operation. So whenever I have two things multiplying, essentially I think of it as one thing, one term. Right? And addition and subtraction separate. So because there's a plus sign between these, I think of this as a separate term. Right? So you think of multiplication as these things stick things together, like they're like glue, while the plus and the minus, they separate things. Multiplication slash division stick things together. Addition, subtraction, separate. So when it comes to isolating things and figuring out how do I keep things on one side that has the variable, things that don't, the first thing you want to do, anything that's separated by addition or subtraction, get rid of them first. Because the variable is really attached to the term it's multiplied by, so you have to move everyone else from around it, and then you deal with that separately. And that you can deal with by doing a division after you do all the other things. So, linear equations typically very easy to get, so let's just jump into some examples with that. But that's a good thing to think about, I think, a good idea or concept. Multiplication sticks things together. Pluses and minuses separate things. So on the left side here, I can think of there as two separate terms. Examples. So these are all linear equations, it turns out. One thing you notice about a linear equation is that the variable has the power 1, and there's no other power of the variable other than the power 1. This is called linear. Let's just jump through this so we can get to the good stuff. 2x plus 1 equals 5. What do you want to do? Well, first, you put your eye on the variable. I want to solve for that guy. But of course, he's connected to that guy. Which means the first thing I want to do is I want to separate the things that have the variables from the things that don't. How do I separate the plus 1 from that side? Well, you do the opposite operation. Now, I'm going to do this one time because it's actually a habit that I don't really like very much. You can write minus 1 underneath here to tell yourself that you're going to be subtracting 1. Minus 1 underneath there. Tell yourself you're subtracting 1 from both sides. This is me taking advantage of property 1, the idea that I can add something to both sides of an equation and it will maintain the solution set. So in this sense, the ones die, they kill each other, and so I only have 2x here. On that side, 5 minus 1 will give me 4. So I had an addition, I did the opposite operation. 1 was added, did opposite operation. i.e. subtracted 1. Right? That brings you to this step over here. Now, here, again, you want to isolate your variable. It is attached to this 2 via multiplication. And so now, multiplication is what's there, which is that. So we think of division as being the opposite of multiplication. And so what I can do is I can divide both sides by 2. So now I realize that 2 is being multiplied. So divide both sides by it. That leads us to another situation where here the 2's would cancel, and now I would have x equals 4 divided by 2, which is 2. This here is the solution because it has the right form. It has the variable by itself on one side, the equal sign, and there's something on the other side without the variable in it. This equation is solved. So x equals 2 is the value of the variable that makes this original statement true. And basically, what I focused on was separating everything that wasn't attached to the variable, then getting rid of everything that is attached to the variable. This is me applying property 2. Even though property 2 is stated in terms of multiplication, you can realize that dividing by 2 is the same as multiplying by a half. So I'm actually applying property 2 here. So property 1 was applied here, property 2 was applied here. This gives me the convenient situation where I can talk about my solution set. So the 4 things I mentioned are the 4 things you're allowed to take advantage of when it comes to solving equations. Okay, now that took a really long time. Let's get through the others quickly. Because again, the linear ones tend to not be too much trouble. Okay, what do you want to do here?
Add 2x.
Add 2x, right? So I can move the 2x over. This will give me 5x here. Just take a step, I guess. So we added 2x, then what?
Subtract 5.
Subtract 5 from both sides. Then divide by 5. So that's the solution. So again, we want to isolate the variables, separate the things that have the variables from the things that don't. The variable is in 2 locations. The goal is to put them all in one location, and then everything that doesn't have the x in the other location, and then isolate the variable. Okay, what do we do now? You can add 1/2. What's 2/3 plus 1/2? Right. 2 times 2 is 4. 3 times 1 is 3. 4 plus 3 is 7. This times that is 6. So that's 7 over 6. So then I get 3 over 4x equals 7 over 6. And what is x? Right, multiply by 4 over 3 on both sides. That'll kill that guy. It's an equation, so I have to do it to both sides. So now I just left with x here. And over here, huh? 14 over 9, because we would simplify first. Don't forget the lessons that we picked up last time. 2 into that goes 2, 2 into that goes 3, so that's 14 over 9. Right? So don't just multiply the 7 and the 4 and the 6 and the 3. You get something larger that you have to reduce later. Simplify before multiplying. That was a lesson we learned last class, maybe the class before, I don't remember. It's all a blur at this point. That's the life of a math teacher. You say the same things over and over and over that you forget when you said them to who. We said it at some point. I for sure said that before. So we reduce before we start to multiply. It makes our lives a little bit easier. I wanted to do another way here, which when we talk about rational expressions, this is going to be very handy. Sometimes, especially if you don't like to work with fractions, you can get rid of them. So one thing you can do is if you have a bunch of fractions in an equation, you can multiply it through. Now remember, without an equation, you multiply and divide by the LCD. With an equation, you multiply both sides by the LCD. Right? So what I could actually do here before I start doing anything is realize that 2, 3, 4, the LCD is what? 12. I could just multiply this entire equation by 12 before doing anything else. And so 12 times this, the 4 is going to cancel. That leaves me with 9x. 12 times that, the 2 cancels into the 12, leaves me with 6. 12 times this, the 3 cancels, gives me 4. That leaves me with 8. You end up with another equation that is equivalent. And I'm in fact taking advantage of property 2 here. And it's just not totally, it's the same equation. It's just that I've put it in a situation where I don't have to worry about fractions. So now I can have 9x equals, add 6 to both sides, that will give me 14, and then divide both sides by 9, I will get 14 over 9. So you get to the same solution, but if you find fractions a little bit annoying, you can kind of avoid them here by doing the LCD. And again, and for emphasis, multiply both sides. When you have an equation, you do the same thing to both sides. If you don't have an equation, you have to do to top and bottom, multiply and divide, or something like that. Right? It's a different process altogether, even though people always mix them up. 4x plus 0.6 equals 1.2. Yeah, you can do the same idea. Decimal point just means over 10, so I can multiply both sides by 10 to get rid of the decimals. Now, you could do the problem with decimals, but it's slightly less annoying. So multiply by 10, it moves it to the one place to the right, moves this one place to the right, moves that one place to the right. And so we would end up with 4x plus 6 equals 12. That looks exactly like the linear equation form that I mentioned at the beginning. Subtract 6 from both sides, then divide both sides by 4. You can reduce here. That's the equation. Now linear equations will always have like either one solution. That's just a property of linear equations. And talk a little bit more about higher orders a little bit later. Okay, E. What do we do now? multiply first because we have to do PEMDAS. So before I start moving anybody, I'm going to multiply this out. This is 6x minus 2. Now, 5 and the 2 can combine. That will be plus 3. This is the term that has x separated from everyone else. Leave that alone, subtract 3 from both sides. And then I can divide both sides by negative 6. Which becomes negative 3. So x equals negative 3. And that's linear equations. Nothing else to teach there. But a lot of the times, the higher equations that are not linear, a lot of times you break them down to linear equations in order to be able to solve them. Nonlinear equations. Equations that are not linear. Okay, I want to break it up into 2 types. 1. Equations where the variable is in one location or in several locations in like terms. So in a linear equation, the power of the variable is always 1. Once you have like an x squared or an x cubed or an x to the half, it's not linear anymore. And you have a couple ways you can look at that. Is maybe you have an x squared, but you have an x squared in several places, and it's always just x squared. It's always a like term. Then these behave a lot like linear equations. You can just isolate the variable as before. Let's look at some examples here. Because they behave a lot like linear equations, there's not much to actually talk about. So you have like x squared equals 4, or you have two x cubed equals 8 minus x cubed. These are nonlinear equations because the x has a power that's not 1. However, the variable is either in one location or it's in several locations, but all locations are like terms. It's always x to the same power. Either of these cases, you can treat it pretty much exactly like a linear equation, except for the last step. You have one additional step. So 8. What you can do is you can raise both sides to the same power. This is a complicated application of the multiplication property, but I'm not going to go into that right now. So what you can do is you can actually raise it to the half power on this side and raise that to the half power on that side. This allows things to actually cancel by the laws of exponents. So by doing that, I end up with x here, and over here I end up with a 2, which is the square root of 4. One caveat is there are 2 possibilities here. And so whenever raising to an even root put a plus or minus sign. And the reasoning for that is, if you look at the picture of something like this, an even-powered thing will often have several locations giving you the same value. So if you want the x squared to give you 4, well, here's your 4. You'll notice that there will be 2 locations from which you can get that 4. You can either square positive 2 or you can square negative 2. And so that's the case. Now, if it were, this wasn't planned, but if you have to raise something to an odd root, you don't have to worry about this. So like x cubed equals 8, I can again raise both sides to a power, which is in fact a root, which is the cube root. That will leave me with x equals 2. We do not need the plus or minus. And that's because of how odd roots behave. If you have like x cubed, it actually looks like this. There's actually going to be only one scenario where you actually get 2 as the answer, 8 as the answer, and that's going to be a 2. The other side is going to give you a negative 2, which does not solve the original equation. And that's a general thing. We'll probably talk about this later. X to the n standard form always looks like this when n is even, and x to the n, if n is odd, it actually always looks like this. Now, I mean if you only have an x to the n. If you have other terms being added, the graphs will change. But other than that, if you have like just a plain old x squared, x to the 4th, x to the 6th, x to the 8th, they all shape like this. The difference is the curve gets wider, right? So you'd have like an x squared is like this guy, and an x to the 4th is like that guy, and an x to the 8th is like that guy. They just get wider, but they all shape like a basin. Versus x to the n when n is odd, so you can have like your x cubed, which is here, and then you can have your x to the 5th, that's going to be a little wider, and so on and so forth, right? But they'll all have that shape. And so what you realize is, to get any number from an even power, there are 2 options, but to get any random number from an odd power, there will only be 1 option. And so you kind of just know that when you're going in and doing something like this. Okay. But it only works for even roots, not odd roots. Here. So here, nonlinear equation, because your x has some power other than 1, doesn't look like the form we mentioned before. However, it's like terms in every location that the x appears. So here I have an x cubed, here I have an x cubed. The coefficients might be different, doesn't matter. Like terms only cares about the variable parts and their powers. So now, we can pretty much treat it like a linear equation. Isolate the variables. So get all the guys with the variables on one side, all the guys without them on the other side. So what you can do is you can say add x cubed to both sides. So you have 2x cubed plus 1x cubed, that's 3x cubes. And then you can divide both sides by 3. And then you can raise both sides to the 1/3. You can use the properties of exponents here. Raising a division to a power is raising each individual part to the power. So that's 2 over the cube root of 3. and that's x. Questions on that? Yeah.
Could you just take the cube root of 3x cubed? You have to move the 3 over first.
Well, what would happen if you took the cube root of 3x cubed? Let's do that. So in this situation, if I have 3x cubed equals 8, could we take the cube root of both sides at this point? You actually could. But you'd still have to clean up after it, right? So this will be that. Notice that your variable still isn't isolated. It still has this thing attached to it. So you're still going to have to go through some work of separating those two, which you can use the law of exponents. So you would get the cube root of 3 times this is going to cancel. That gives you x equals 2. And then eventually you'll divide both sides by that. You'll get to the same answer. So you do have some leeway, but ultimately you do want to separate the x's. So it's probably just easier to just separate it from the beginning, and then if you have to simplify on the right side, it's fine. Yeah.
Why is the radical in the bottom? Like, aren't radicals not supposed to be?
No, we don't care. I think I also mentioned that before. That whole thing about, oh, radicals shouldn't be in the denominator, that's not a thing. But I don't know why they tell kids that. You know, kind of like when you were younger, they're like, you can't subtract a bigger number from a smaller. Do you remember people telling you that when you were a baby? Like, you have 5 toys. You can't take away 7 toys. You only have 5. And then now it's like negative numbers. Like, what the hell are they talking about? Yeah, it's the same kind of thing. Like, radicals in the denominator, we don't actually care. It's just sometimes you might want to simplify something, and for that reason you might want to get the radical out of the denominator. But that could also happen in the numerator as well. Sometimes you don't want it in the numerator because you want to simplify. But yeah, that will be fine. I wouldn't care. So this idea that radicals in the denominator are ugly or having negative powers, you don't want that. It's not a thing. Don't worry about it. You could even write this as 2 over 3 to the 1/3 power. I'd be fine with it. You could write it as 2 times 3 to the minus 1/3 power. I'd be fine with that as well. No one really cares at this level. Okay, the second type. Nonlinear equations. Where the variable is in unlike terms in several locations. So if you look at an equation, it looks linear. You just do pretty much straight up one of the 4 properties that I mentioned earlier, and it's going to be easier to separate things with pluses or minuses by doing the opposite operation, etc. Unlike if you have nonlinear, where you only have like terms, you can treat them pretty much like linear. Separate everybody, and then do that. Now, when you have the variables in unlike terms in several locations, the strategy is a little bit different. I also do want to point out, and sometimes for me it's actually preferable. So the case that I said you could pretend it's linear, the strategy here will also work over there, and in many times it's actually preferable because then it tells you when, it describes to you exactly when you need the plus or minus versus when you don't, instead of you having to think of this extra. So let's actually do that. Here's the strategy for this situation. Nonlinear, unlike terms, main strategy here. One. everything to one side. For definite, let's say left. Two, factor the left side. Three, apply the zero factor property. Four, if necessary. It might not be necessary. Apply a previous strategy, like the linear strategy. To isolate the x, or whatever variable you're using. That's the strategy. So this is the general strategy for solving an equation. The goal is to factor. Factoring is very important. Bring everything to one side, factor that side, apply the zero factor property. Because everything's on one side, you're going to have zero on the other side. So when you factor them out, you have a bunch of factors being multiplied equals zero. The zero factor property is going to say one of the individuals, or some of the individuals, or all of the individuals have to be zero themselves. So you'll set each individual factor to zero. This will bring you to an equation of a lower order, usually linear, but not always. But you deal with something smaller, and then you isolate the x according to the previous strategies. Yeah, that's it. So that's a main strategy here for solving equations. You think factor. Some examples here. This wasn't planned, but let me redo x squared equals 4 e, just to show that it can work with the previous strategy. At this point, I'll just do a few examples because we'll be using that strategy a lot more. It's a very important strategy. Factoring and using the zero factor property. Bring everything to one side so there's a zero on the other side. Factor the side that everyone else is on. Use the zero factor property. Now, this strategy here, we could just square root both sides. Another way to look at it is to bring everyone to one side. So if I bring everyone to one side and then factor, what happens? That's the difference of squares. So I have x minus 2, x plus 2, and then I can apply the zero factor property, right? If a times b equals 0, then either a must be 0 or b must be 0. That's the only way to get 0 by multiplication in the real numbers. So this means your x is either 2 or your x will be negative 2. So it can be plus or minus 2. And here you didn't have to remember to artificially put in the plus or minus. By doing the factoring version, you will get all the guys you're supposed to get in the first place. And you don't really have to worry about, should I be putting a plus or minus or not? You won't have to worry about it. The factoring will take care of that for you. So there are times when, strictly speaking, you don't need to factor, but it's probably actually preferable that you think of it in a factoring way anyway. So pretty much the only case where I would say you don't really have to think factor is the straight up linear case. In every other case, you can do the factoring strategy, and it'll actually help you not to miss anything. what do we do here? Add x to both sides, because we're going to strategy once to bring everyone to one side. Just to be suggestive, I'll line it up in the middle. Now what?
X plus 3, x minus 2.
Right, now you factor. So this one we know how to factor. Plus 3 minus 2. And then you apply the zero factor property. So this is x plus 3 equals 0, or x minus 2 equals 0. And so that means your x equals minus 3, or your x equals 2. And you can, again, just see the strategy at play here. Bring everyone to one side. To one side. The factor. Zero factor property. Now I know a lot of you just do this naturally, but I do want to emphasize that every step had a reason. And there are times where if you just go through something and not really think about what you're doing, once things get slightly more complicated, now you just don't know what to do. Really, I know it might seem simple to you, but really understand what's going on in the simple case. You understand the simple case, the harder case is just an application of several simple cases. Right? So really understand why this step, why that step, why this step. This is what I was doing. There's a strategy in my head that I'm going through. Okay? So at any given time, I know what it is the next thing to do. You don't want to be in a test or a quiz and be like, what should I do now? What did you want to do in class again? You've done messed up. You're not studying right. Right? You're in a situation, you should immediately know, oh, I'm in this situation, the next step would obviously be this. And then the next step needs to be that. The next step needs to be that. And then you just worry about making sure your algebra is correct on each individual step. You'll never actually be lost or not know what to do. I need to solve this equation. A bunch of things all over the place. It's nonlinear. What should I do? Panic? No. Bring everything to one side. That's the first step. Once you're there, what do I do now? Factor, right? And what do I do now? Zero factor property, right? It seems obvious at this level, but trust me, the things that look uglier than this, it's the same strategy. So learn that strategy well, very important strategy. Okay, what do we do now? Factor by group. So again, we know bring everything to one side. And it's already on one side, so now I just need to factor. It has 4 terms in it, so factoring itself has a strategy. So sometimes you want to realize that you're doing one overall strategy, but at some level in the middle, there's another list of strategies that you have to do. Like factoring itself has its own strategy, right? I gave you the list of things into factoring. So when you're looking at something and you know the next step is to factor, you have to figure out what technique in factoring would I use. Here you're going to notice, oh, there are 3 terms, so it's definitely not difference of squares or any of that. There's no GCF. There are 3 terms, it looks like a quadratic, so I'm going to do like the AC method or the trial and error, and that's how I got to this step. Here, I know I want to factor. There are 4 things. Factor by grouping is going to be the thing I think about first, other than factoring out a common term, which there is none. So I would factor out an x squared from here, and a minus 1 from here. Now I have the same thing left in the parentheses. I can factor that out. What can I do now? This can factor further. That's the last step of factoring. Once you apply your technique, look if you can go further. And so this one can't go further, but that one's the difference of squares. So now I apply the zero factor property. So everything was already on one side, so the goal was to factor. I did that in these 3 steps here, doing factor by grouping. Now I'm going to say either x plus 2 equals 0, or x minus 1 equals 0, or x plus 1 equals 0. And eventually you'll be able to even skip that line and just jump straight to x is minus 2, or x is 1, or x is minus 1. Again, you can notice that if you were to plug in any of those guys into the original, that would actually be true. Right? If I plug in 1, I would get 1 plus 2 minus 1 minus 2, 0.
Do we do with extreme solutions? Like it's not like one of them is not equal.
Yes, but that won't happen in a case like this. That will happen if things like you have a radical, or you have there's an x in a denominator or something like that. You'd have to worry about things like that, because you know, like if there's an x in the denominator, it can't be 0. So if you get 0 here, you have to throw it away. We're not at that stage yet, but that's coming. We have to worry about that before. Here's a common type of mistake that I see sometimes. Like doing this here is kind of obvious because I even wrote it suggested, but there are times when an equation might appear and it might look something like this. And of course, now we know the strategy is bring everyone to one side and factor. There are times when students don't remember that that's the strategy. And then they do something like this. They tried to, that was a square. So they factor out the square here and x plus 2, and then they're like, oh, I can divide both sides by x plus 2. So then I would get x squared equals 1, and then my x is plus or minus 1, right? Now that is the wrong thing to do. Obviously you can see we missed somebody, right? And why did we miss somebody? Because you disobeyed the strategy, is the short answer. The other answer is you actually, because x equals minus 2 is a possibility, you divided by 0 at one point here, right? Like in the situation where x equals minus 2, which it could be, you would be divided by 0. And that messes everything up. Anyway, the moral of the story is know the strategy, follow the strategy. Like just do the strategy all the time. You might see some other mathematical operation that you could apply at the time. If it's not in the strategy, don't do it. Things can happen, like where it doesn't seem like I'm doing anything illegal, and so this is why students feel confused. Like, I felt so good on that test, I don't understand why I did so bad. Because what they're doing doesn't really feel wrong. I mean, that's done correctly, they divided by x plus 2 correctly. Like, why is this the wrong answer? Because you didn't follow the strategy and hence lost the solution. Right? There's a reason why the strategy is written the way it's written. Follow the rules. You see stuff on both sides, bring everything to one side. Don't start dividing and doing blah, blah, blah. Bring everything to one side. So this would be the wrong way to approach the problem. You actually miss a solution. Okay? So that's a good strategy. Bring everything to one side. Step 1. Factor is step 2. Zero factor property, step 3. Right? Factoring in and of itself has 4 steps in it, depending on what things look like. But don't go and just try doing whatever you do just because it feels right at the time. That's how people get in trouble. Okay, let's talk about quadratics. These are actually very common, very useful, very important for us to be able to solve. these are equations of the form. Ax squared plus bx plus c equals 0. This is called a quadratic equation, where a, b, c are constants. Can be a little bit more general, or expressions without the x. And a is not 0. Because if a is 0, that's just a linear equation, right? So the a has to not be 0 in order for it to be quadratic. So the main strategies here . One, the factoring strategy. This is in fact the preferred strategy. If you can get this to work, do that. Another option is something called completing the square, which we will be talking about in its own right. At least when I talk about circles. We're not going to do that much for solving quadratics. The third thing is to use something called the quadratic formula, which is in fact derived via completing the square. So I'll probably do that for you. So those are the three main strategies, and I would try this. If it doesn't work, try that. So when it comes to solving quadratic equations, either try to factor. If it doesn't work, just jump into the quadratic formula. Completing the square isn't worth it, at least from what I can see. In fact, the quadratic formula was derived by completing the square. So if you do completing the square, it's kind of like you're manually doing the quadratic formula instead of just jumping to the last step. Probably not worth it most of the time. Completing the square is important though. There are contexts in which we will be forced to actually do it. So we will talk about it and how to do it. But for solving an equation of this form, either try to do the factoring method and use the zero factor property or the quadratic formula. Examples. A. Okay, first one. Gonna try to factor. Does it work? Well, two numbers that I multiply get 6, add and get positive 5, plus 3 and plus 2 seem to work. And so I would get x equals minus 3 or x equals minus 2. Something like this, the 5x squared equals 20x. If you divide both sides by x, you're wrong. You are also missing the solution. Follow the rules, bring everything to one side, then factor. GCF factoring works here. 5x is the common term. X minus 4 will be left over. And so this means that either 5x equals 0, which means x equals 0, or x equals 4. For you guys, you can try these right now. I'm just gonna write down 2 problems for you to try. But next time I do it in class, I'm going to first talk about the quadratic formula, where it comes from, and then I'm going to do these. But you guys can probably just do them right away. You guys probably know the quadratic formula already. So C. We can get solved there. Absolute value equations is another one I want to talk about. But yeah, we'll do that next time. Try these for next time. Next we'll talk about equations with radicals in it, equations with rational expressions, and equations with absolute values. You need to know how to deal with all of them. Okay, take care. See you next
For the
week.
ones on the board, you said you want us to use the